For centuries, astronomers looked up at the night sky and made a very logical assumption. They saw bright points of light separated by vast expanses of black and concluded that the space between the stars was a perfect, empty void. But this data visualization highlights a mathematical problem. We know massive stars burn through their fuel in a few million years, yet our galaxy has been birthing new stars for over 13 billion years. Where is it getting the raw material? The Interstellar Medium, or ISM, fills this darkness with a churning, turbulent ecosystem of gas, ionic plasma, and microscopic dust that permeates the entire galaxy. We've even built machines to touch it. In 2012, the instruments aboard Voyager 1 recorded a sudden shift in plasma density. That measurement physically confirmed the probe had left our solar system and crossed directly into the interstellar medium. By mass, the ISM makes up an enormous reservoir of matter. It acts as the physical bridge connecting the life cycle of a single, isolated star to the ongoing survival of the galaxy as a whole. Within this vast interstellar environment, there are localized pockets where the cosmic gas and dust gather into massive, dense structures. Astronomers call these regions giant molecular clouds. Gas clouds balance gravity pulling inward against thermal pressure pushing outward. In deep cores near 10 Kelvin, outward pressure collapses. Gravity crushes the gas into an ultra-dense core. To conserve angular momentum, the cloud spins faster, flattening into a whirling accretion disk. In structures like the pillars of creation, we see this exact physics playing out across light years. These towering dust columns are active stellar incubators. In these dark, cold, and quiet pockets of the universe, gravity can finally take hold. The most desolate places in the cosmos provide the exact physical conditions required to conceive the next generation of stars. Before an infant star ignites the stable nuclear fusion that powers it for billions of years, it goes through a volatile infancy known as the Tauri phase. Rapidly ingesting material from its spinning disk, the forming star chokes on the gas, blasting beams of high-velocity plasma outward from its poles. These intense stellar winds act like a cosmic snowplow. They tear through the dense cloud, carving cavities into its birth cocoon. With the dust cleared, the intense light from the exposed infant star can finally escape. That light scatters and bounces off the microscopic dust grains lingering in the immediate environment. Astronomers call this illuminated cloud a reflection nebula. Because microscopic dust scatters shorter wavelengths of light so efficiently, it makes these nebulae glow with a distinct, brilliant blue signature. A star's very first act is the violent destruction of its own incubator. That outflow of energy sweeps through the interstellar medium, churning the environment for whatever forms next. Millions of years later, a massive star exhausts its nuclear fuel. Without the outward pressure of fusion, the core collapses inward, triggering a massive shockwave that tears the star apart in a spectacular supernova explosion. In its life and the extreme heat of its death, the star forged heavy elements like carbon, oxygen, and iron. The explosion blasts this enriched material outward into space at thousands of miles per second. This violent expansion creates the hot ionized phase of the interstellar medium. The advancing shockwave superheats the surrounding dormant gas to millions of degrees. This animation shows how the expanding wall of energy acts like a cosmic plow. When it rams into the edge of a nearby cold molecular cloud, the sudden impact instantly compresses the gas inside. The explosive death of one star directly provides the raw chemical materials and sudden gravitational compression required to trigger the birth of the next. Zooming out to view the Milky Way in its entirety reveals a massive, closed-loop mechanical system. The ongoing friction between dying stars and the interstellar medium dictates exactly how fast a galaxy depletes its available gas. That delicate balance ultimately determines the total lifespan of the entire galaxy. Every iron atom in our blood, every water drop in the oceans, and every rock beneath our feet was forged inside a star, blasted into the interstellar medium, and scooped up by gravity millions of years later. We've deployed instruments like the Hubble Space Telescope specifically to peer into these dusty nurseries and explosive remnants, capturing the ancient light of this cosmic recycling process in action. This massive reservoir of matter serves as the active, immortal protagonist of our universe, ensuring the galaxy is never truly dead as long as the cycle continues.